Deep 600 meters beneath the solid rock of the Alps, thousands of workers are racing against time to complete a massive pumped storage hydroelectric mega project, Limmern. They have to work continuously in 3 shifts every day in an enclosed, low-light, and heavily dusty environment. The biggest challenge is having to constantly reinforce the rock walls to withstand immense geological pressure, deal with the risk of cave-ins from all sides, and find a way to transport machines weighing hundreds of tons to an altitude of thousands of meters in a terrain with absolutely no roads. So, how did the engineers do it? Let's find out in detail right now. But before getting into the video, don't forget to hit the like button and share this video to spread it to more viewers. And now, let's get started. The core purpose of this massive complex is to create a natural battery to regulate the power grid. The operating principle is based on circulating water between 2 reservoirs, Lake Limmern in the valley below and Lake Mutsi, located at an altitude of 2,474 meters. When electricity demand is low, the system pumps water back up to the top of the mountain. When electricity is urgently needed, the water stream will be discharged steeply downwards, generating a power output of up to 1,000 megawatts. However, the most difficult problem is how to connect these 2 lakes. With vertical cliff terrain and freezing temperatures in winter, laying pipes on the surface is impossible. The only solution is to drill right through the core of the mountain. To do this, the volume of work is absolutely enormous. The workers must drill, blast, and clear out about 800,000 cubic meters of hard rock from the mountain. This massive empty space is exactly where they will build the entire underground tunnel network, including 2 vertical pressure shafts and a vast central cavern to house the power plant. To create the massive underground space inside the mountain, the tunneling work is divided into 2 separate categories, requiring engineers to apply specialized construction methods. The first category is the Cavern, the central cavern housing the power plant, which is the size of a 15-story building, 150 meters long, 30 meters wide, and 53 meters high. Here they applied the controlled delayed blasting technique combined with the NATM tunneling principle. The process takes place in a closed loop. First, jumbo multi-boom tunneling machines enter the tunnel face, drilling dozens of deep holes into the rock face according to a computer-guided layout. Explosives and delay detonators are loaded into them. When activated, the explosive clusters detonate milliseconds apart. This technique helps break the rock mass exactly to the design profile, while simultaneously neutralizing the shock waves to prevent fracturing the mountain structure. As soon as the ventilation system sucks out the smoke and dust, excavators and bulldozers immediately move in to clear thousands of tons of rock and soil. At the same time, a continuous reinforcement process is activated so the rock face is not left exposed. Engineers quickly inspect and treat the surface. Welded wire mesh is immediately attached to the tunnel wall, closely followed by robotic arms spraying a high-pressure concrete layer, shotcrete, covering the entire structure. Finally, thousands of steel rock bolts are drilled deep through the concrete layer and right into the geological stratum. This outer shell compresses the geological faults, utilizing the very stress of the surrounding rock to turn the mountain into a massive, self-supporting arch structure. The second category is the construction of 2 pressure water tunnels connecting Lake Mutsi down to the plant. With a steep incline of 40 degrees, the conventional blasting method cannot suffice. The solution devised is using a specialized 140-meter-long TBM, tunnel boring machine. This machine operates on a bottom-up reverse excavation mechanism. The massive cutter head with ultra-hard alloy discs continuously crushes the rock face. The thousands of tons of debris generated are not transported by trucks, but discharged directly down a hopper system by gravity and taken out by a conveyor belt at the base of the tunnel. As the TBM advances, the tunnel walls are immediately reinforced with high-strength H-beam steel rings, preparing for the pressure-bearing steel lining step. Throughout the construction process of both these categories, the greatest risk always lurking is the high-pressure groundwater system. At depths of hundreds of meters, water continuously erupts from geological faults. If left uncontrolled, they can break the sprayed concrete structure and submerge the entire construction site. The conventional method is to drill probe holes and pump high-pressure cement grout deep into the rock face to seal the underground veins. However, at the Limmern project, the pressure and flow rate of the groundwater are so strong that it easily breaks apart and washes away the conventional cement grout layer before it can set. To solve this problem, engineers were forced to add specialized polymer-based compounds to the pumping grout mixture. When in contact with water, this polymer chemical creates an instant reaction, expanding its volume manifold and hardening almost immediately in just a few seconds. This chemical glue layer forms a perfect plug, completely sealing all leaking cracks, isolating groundwater from the construction area. Another interesting point about this project is that all 800,000 cubic meters of excavated rock from the underground tunnel system are maximally utilized. Instead of being transported away for disposal, they are brought directly into the high-capacity crushing plant system to be used as the core material for pouring concrete to build the Mutsi Mega Dam at the top of the mountain. Returning to the underground system, after the drilling and excavation work is finished, the entirety of the 2 water tunnels will be lined with steel pipes to withstand the massive hydrodynamic pressure from the 600-meter-high water column. Hundreds of super-heavy steel pipe sections, each weighing 30 to 40 tons, are slowly lowered by a cable winch system down along the 40-degree incline tunnel. After being welded into place, the gap between the steel pipe shell and the rock face will be backfilled with concrete. This technique helps lock the pipeline tightly, forcing the natural rock mass to share the pressure with the steel shell. At the same time, inside the central cavern, another massive construction site is taking place to prepare for the mechanical installation phase. Looking at the actual construction footage, we will see thousands of workers weaving giant steel cage systems and continuously pouring solid concrete blocks. In reality, the giant cavern after excavation is just an empty space. To have room to place the 4 pump turbine units, the engineers had to build an entire multi-story reinforced concrete plant structure right inside the mountain. This massive volume of rebar and concrete serves 2 utterly important duties. First, it creates the mold to encase the steel spiral casings, where the high-pressure water stream will rush in. Second, and most importantly, it acts as a super dense foundation block. This concrete foundation is tasked with anchoring the entire mechanical system, weighing thousands of tons, and absorbing all the horrific vibrations when the turbines spin at high speeds. Only when these concrete foundation blocks have set and reached sufficient load-bearing strength can the final core phase begin, transporting and assembling the massive machines into position. But how to transport these super heavy and oversized machines deep into the mountain when the construction area has absolutely no access roads? To solve this problem, the engineers established a combined logistics system, utilizing a giant outdoor aerial cableway traversing the slopes of the Alps, connecting with an underground funicular railway system with a payload of over 200 tons piercing straight into the heart of the mountain. Every single giant component, such as spiral casings or transformers, is loaded onto this system and inches meter by meter into the central cavern. Once the challenge of transporting the ultra-heavy equipment was solved, engineers immediately began the assembly process. Inside the central cavern, the 4 hydroelectric units were assembled from the bottom up, using an overhead gantry crane system. Located at the lowest level are the massive spiral casings. These are welded directly to the penstocks and completely encased in concrete to bear the load. Directly above this, the crane system lowers the turbine runner and installs the vertical drive shaft. With the turbine section complete, they face the ultimate technical challenge: assembling the generator unit. The crane must lift the massive rotor, weighing over 330 tons, and slowly lower it inside the stationary stator ring. The clearance between these two components is measured in mere millimeters, requiring absolute precision to avoid damaging the magnetic structure. Finally, the generated electricity is stepped up to 380 kilovolts by transformers to be integrated into the national power grid. Once the entire system is ready, the water valves are opened. The tremendous kinetic energy of the rushing water can push the plant's capacity to 1,000 megawatts, equivalent to a large-scale nuclear reactor. Unlike thermal power plants that take hours to start up, Limmern can reach this maximum capacity from a standstill in under 3 minutes. The facility acts as a rapid response backup power center, ready to instantly discharge electricity to compensate the European grid whenever wind or solar energy generation drops. The Linth-Limmern hydroelectric plant is a practical engineering solution for energy storage. This massive underground facility provides mandatory stability for the power grid, especially as renewable energy sources become more common. Which construction phase of this project impressed you the most? Leave a comment below. Do not forget to like, subscribe, and turn on notifications to watch more analytical videos on engineering mega projects. Thank you for watching, and see you next time.